Okay, before we start on the notes, I wanted to give you guys a chance to ask questions if you had questions on yesterday's problem set, but I'm sure you all did, right?
Yes.
All done. So, any questions on there? I don't want to just put up the answers because then you guys will just start writing and not. So, what did you think on number one? Which of those looks like a scatter plot that would show our linear model is a good fit? A, B, or C?
C is that fan one.
C is the fan one. Okay. So this one shows the best random scatter. So part A, this should be the one that indicates the linear model is a good fit. This one we see a curved pattern. Here we see that fanning pattern. So these two, the linear model is not a good fit because there's a pattern in the residual plot. Here, randomly scattered residual plot, we have a good fit for a model. Okay. And then we're just interpreting slope. You guys should be good at that by now. Making predictions. So I'll put this up here if you want to. I'm not going to leave it up like for just to write it down, but it'll be on the notes video. So if you want to go back and check it, it will be there for you to check. So. Okay. So for today's notes, you should have this half sheet in your folder. So we've had, on the last quiz, we had two different ways of getting a regression equation. Now we're going to be adding a third way to get to it. The first one was using data. If we're using data, we will enter the data into L1 and L2. Then we do stat, calc, and then number 8 when ready. And that will give us all the information we need to write our equation. Okay, so you guys should already know that one. The other method, it could be that we're using the summary statistics. So if we're doing that, we find the slope is R times standard deviation of Y over standard deviation of X. To find the y-intercept, we do y bar, so the mean of the y variable, minus the slope times x bar. So both of those you've already been quizzed over, you should know them. Okay? Today we're going to be adding in our third method, and this is computer output. Often in a real world situation, if people are doing a statistical analysis, they use computers to do the analysis rather than a calculator. Because you'd be dealing with really big data sets, and it's a lot easier to enter it on a computer than on a calculator. And it can handle really big data sets, and you can download them, you can share it, all that is a lot easier on a computer. So we need to be able to read computer output and find the values that we need. So that's what we're going to be looking at today, is how do we find this on computer output. And we're also going to be adding in a couple of other variables and talking about what these represent and how to interpret them. So that's also going to be in today's lesson. But computer output is kind of our focus. So in our first example, we have Lydia and Bob. They were searching the internet to find information on air travel in the United States. They found data on the number of commercial aircraft flying in the United States during the years 1990 to 1998. The dates were recorded as years since 1990. Thus, the year 1990 was recorded as year 0. They fit a least square regression line to the data. The graph of the residuals and part of the computer output for their regression are shown here. So, here's our residual plot. So what do you notice about that? Do you see a pattern? No, not really. So what does that tell us? Here's part A. Is a line an appropriate model to use for this data? Yes. So we're going to say yes, it is appropriate because the residual plot does not show a pattern or is randomly scattered, however you want to say that. So anytime they're asking you if a line is appropriate, that's what they're wanting you to do, is check the residual plot and comment on whether there's a pattern or it's randomly scattered. Okay. Part B, we're wanting to write an equation of the regression line. So here's where we get the information from the computer output. So when we look over here, in this first column, we see constant and we see years. You will always have this word constant in every kind of computer output that you look at. We have really about 3 different computer programs that we're going to look at their output, and it's all just variations of the same information, but this word constant is always there. So if you think about our equation for a linear model, the constant is just the number without a variable. So which value, if we're talking about slope or y-intercept, which one of those would be the constant? I thought that was an easy question. So the constant is your y-intercept. So when we look at constant and we look over here, this value is the y-intercept. If we're talking about the coefficient of this is my x variable. So the coefficient of x is the number multiplied with x. This value is my slope. So anytime you see constant, you're going to see constant and you're going to see a variable name. The variable name is always your x variable. The coefficient of that variable is your slope. The coefficient of constant, that's your y-intercept. No matter what kind. Sometimes these will be listed in the other order, where the years will be first and then constant. So you're just looking for that constant. So when we write this out, we want to write it using years instead of the x variable. You'll notice it doesn't tell us anything about the y variable. So we're going to go back up and have to look back at our information in the paragraph and say, what are we trying to predict? We're using years to predict something. What is the other variable we're interested in? That's what we're looking at. This is the data that they found. They were tracking the number of commercial aircraft flying in the United States. That's our y variable. So, when I'm writing this out, I'm just going to call this aircraft. Okay, just to make it shorter than writing all of that. So aircraft is equal to the y-intercept plus the slope times the x variable, which is years. So all of that information came from either the paragraph or the computer output. Everybody able to see where we got the numbers and how we got all that? Okay, so now we're going to interpret the value of the slope in context of this question. So this is exactly what we were doing before when we interpreted the slope. So we're going to say for each year after 1990, we expect the number of aircraft to increase by this amount. So for each additional is predicted to. We're going to make sure we leave that in there. Increase by 233.517. Okay, now in part D, we're wanting to use our equation to make a prediction. Now, when we do this, we want to show plugging in the value for years. So I'm going to just write out the equation with that plugged in. Now, when I go to plug in the number for 1992, I'm talking about years since 1990. So I'm just going to plug in a 2 instead of plugging in 1992. Right? Because remember, the year 1990 was year 0. So 91 would be 1, 92 would be 2. And then you're just going to do this on your calculator. So do that. I get 6.964 commercial aircraft. Okay, so when we want to know the actual number of aircraft flying in 1992, we can look up here at our residual plot and we can go, okay, that would be year 2. My residual for that year is 40. Okay, so I go to year 2, find the dot, the residual is 40. Okay, so that means when I go to find the actual value, I'm going to do my residual equals the actual, which I don't know, minus the predicted, which I just found. So that will let me solve to find the actual number of aircraft flying in 1992. So just add that over. Questions so far? Is it okay? I went up here to the residual plot and I said in 1992 is the year 2. So then I said, okay, the only place there's a dot for 1992 is up here, and that value is 40. What else? That's a lot of information, so don't. Do you have a question now? Good? Okay, let's look at the back side. So now we have these values of S and R squared. So these are two new values that we haven't talked about before, but we're going to be seeing those in computer output. So when we're looking at these, this value of S is the standard deviation of the residuals. So, if we think about what standard deviation means, standard deviation is the average distance from the mean for each data point. So, if we're thinking about this in terms of residuals, the sum of all your residuals should be 0. Okay, because we have some that are positive, some that are negative. They should be randomly scattered around. So, we should have a sum that is 0. So, if we're finding an average, we add everything up and divide by how many values we have. Well, when we add it up, we get 0. So that average should be 0. Okay? So when we look at average distance from the mean, we're looking at how far it is from 0. So we're looking at how far are we missing by. Okay? So if we think of a residual as the actual minus predicted, so it's how far away is our line from the data values. So this is the average distance it is from the data values. So S tells us the average amount our prediction is off from the actual value. That's what it's really doing, is it's telling us, okay, we're not hitting every value, but this is how close we're getting. So a smaller value of S means our data is tighter around that residual, or the least square regression line. So we have smaller residuals. Our linear equation is a better predictor. So if S is large, that means we're missing by a lot. So it may not be as good a fit. So it's going to show a weaker relationship. Okay. So when we look at our previous example, if we wanted to interpret the value of S, when we look at our computer output, there's S right here in this corner. So our value is 33.43. So here we're talking about the number of commercial aircraft and the number in the year. Okay? So we're saying whenever we make this prediction, so the average difference between the predicted number of aircraft and the actual number of aircraft is 33.43. Just telling us how much are we missing by on average. And when you think about our slope and y-intercept values, those were big, right? Our y-intercept was almost 3,000. Our slope was 233. So if we're looking at 33, that's pretty small in comparison to these. Okay? So you may think, well, we're missing by 33 every time, but we're predicting really large numbers. So when you're predicting something really large, you're going to expect your difference to be a little bit bigger than it would if we were predicting values that were all between like 2 and 5. We're going to have really small residuals there, hopefully. So, so you have to take that into account whenever you're deciding, is that large or not. Okay, so this value of r squared. R squared is called the coefficient of determination. So it sounds really complicated, but it's really not all that. So this is a value that explains what's happening here. So let me. So if we looked at a scatter plot of this data, so years since 1990, and the number of aircraft, okay? If I had a scatter plot of this, I would be able to see a general trend. I would be able to see that there's some things happening here. And I can say, if I have a year and I know what that is, I can kind of predict where I'm going to have the number of aircraft. I can make predictions on that. I can say, well, I think my regression line is going to go right through here. Okay? So I can say in the year 1992, I think it's going to be right here, but my actual is off of that a little bit. Okay? So it's not precise. There's a little bit of error in there. So we have some variation here, because we have some years are close, some years are farther. We have some variation in the number of aircraft. We have smaller amounts and larger amounts. So what this coefficient of determination says, the variability here can be explained by the variability here. So the difference in the number of aircraft is because the year is different. Okay? And it's measuring what percentage is explained by that relationship. Okay? So whenever we write out our explanation, we're going to look over here and we see there's our r squared. It's 99.8. So that's my r squared value, 99.8%. So that's what I'm going to do over here. So I'm going to start with that value. How do you interpret this? So I say 99.8% of the variability in whatever your y variable is. We go next. So in the number of aircraft, can be explained by the variability in the number of years So, when we have a value like 99.8%, that's a lot, okay? Most of the variability is explained by the year, but there's some part of it that's not explained by year. Sometimes we'll have the same year and we may have two different values. We may have two different things here. That part, that difference in here, in the residuals, is not explained by this linear equation. It's explained by something else. So that other 0.2%, something else is causing that difference, but 99.8% of the variability is explained by the year that it's collected, this data was collected. So when we get some number really big, then we're saying this is a pretty good model. This is a pretty good way of making this prediction because we're explaining 99.8% of what causes this to happen. If we had a number like 57%, then we would be saying, okay, we may need to look at another variable that's a better indicator. Okay, but here, this is a pretty good indication. You just want to make sure that you include this word variability both times. It's not 99.8% of the number of aircraft, it's 99.8% of the variability in the number of aircraft. So make sure you include those phrases. Sometimes you will see this written where it's 99.8% of the variability in the number of aircraft flying in the U.S. can be explained by the linear model. So sometimes right here, instead of saying the variability in the number of years since 1990, instead of saying this X part, it'll be by the LSRL, by the linear model. Something like that is okay too. So if you're looking online at other resources, you may see that as the explanation. So just know it's okay to do that. If you see that, it's fine. Okay. Questions on this? Does it seem like a lot of words to have to remember? Sorry. Okay, let's look at example 2. Here we see a consumer organization has reported test data for 50 car models. We examined the association between the weight of the car in thousands of pounds and the fuel efficiency in miles per gallon, and determined that a linear model was appropriate. The regression output is shown below. So here's a different type of analysis. So this was using a different computer program, but you can see a lot of this information is the same. So if we're looking at this output, what is the value of the slope of the equation? There we go. So this value, the coefficient of the x variable, that's your slope. Okay. What is the y-intercept? Right up above there, there's your y-intercept. Okay? So we weren't asked for those, but it's good to think about it and identify them. So here we want to know what does r squared mean in context. So that's this value right here. We do not use r squared adjusted. We're just going to use r squared. So make sure you don't get those confused. So we're doing this one. So we want to explain what does this mean in context. So we say 75.6% of the variability So 75.6 of the variability in the y variable. So we want to go back and look at what is our y variable. So the weight of the car, that's x. So then fuel efficiency, that's the y. Okay. Because whatever is here, that's x. So in the variability of the y, so in fuel efficiency, explained by variability in and this is where we just put in our x variable. So our x variable was the weight of the car. So here we see 75.6% of the variability in the fuel efficiency can be explained by the variability in the weight of the car. So here we have almost 25% of this difference that's happening is explained by something else. That something else is what's left in the residuals. It's the part where we missed by something. The 75.6 is the percent of the variability that was taken care of by the model. That the rest of it goes into the residuals. So that's how we would write that one out. Now, you could be asked here, what is the value of the correlation coefficient? Well, we have standard deviation and stuff, we have T, we have P, we'll get to those next semester. We talked about S, this is the standard deviation of the residuals. We have R squared and R squared adjusted, which we're not going to do in this class. So how do we get R? Square root. We know R squared, we can take the square root of that to get R. Because R squared is, these are related because the coefficient of determination is the square of the correlation coefficient. So if you're given R squared in the computer output, you can take the square root to find R. So my R squared is 0.756 is R squared. So I just take the square root. Usually we'll round to 4 decimal places. Okay. Makes sense? R squared, square root gets R. Now, here's something that is important, and people will miss this, and I'll say, oh, why did you miss that? We talked about it. So pay attention on this part. Remember back in Algebra 2, when you take a square root of something, what do you always have to put in front of the number that's the square root? Take square root of 64 plus or minus 8. It could be positive, it could be negative. So how do we know which way it's going? The correlation tells us about the strength and the direction, right? R tells us about strength and direction. What else in here would tell us about the direction?
Slope.
Slope. So if the slope is negative, R should be negative. If the slope is positive, R should be positive. Okay? So don't forget to go back and check that. People forget that all the time. They'll just go, oh, it's the square root of that. There we go, I'm done. You've got to go back and make sure that the sign of your slope and the sign of R match. So R here is a negative 0.8695. Okay, does this make sense to you?
Yes.
How we're getting that? Okay, so that is going to go page 100 in your notebook. And then your problem set for today is going on page 101. So go ahead and attach those in there. If you didn't do yesterday's problem set, you might want to do that. And then do today's as well.